All right, here is our last lecture for chapter 19. We are on number 85. And looking at this one, starting it off, in case you missed it, it's sort of back. Equilibrium. The value of Ka for nitrous acid is that. So we have a K value. Write the equilibrium expression for Ka. Well, that's pretty easy. Hopefully the rest of the problem is just as easy. Looking at the equation, I'm not even going to bother writing it down. Sort of that whole HA turns into A and H plus, but we know exactly who these guys are, so we'll go ahead and just write it. H plus, it's nitrous acid, it tells us that up above, minus, okay, everything's kind of like a one-to-one, so there's no exponential values for this one. HNO2, all concentrations, and I do have the value, and I'll write that in. Okay, not bad. Part B, by using the value of Ka, calculate delta G, not for the associated nitrous acid in an aqueous solution. So again, this is a really good problem. It's demonstrating that we're relating these two values together. It's not really like a calculation to determine it with some other weird numbers in there. It's a relationship. So we'll go ahead and squeeze this in. I know I didn't leave a whole lot of space here. It's equal to negative RT, natural log of K. And then if we plug in the values that it gives us, because we're going to use the K to get the delta G. All right, so the way I'll write this in here is it is negative. I'll put that up here. I'll say 8.314 times 10 to the negative 3. So changing joules to kilojoules. Just making sure the units are all the same. Kilojoules per mole per Kelvin, if I'm not mistaken. And then multiply times the temperature at 298 Kelvin, 25 degrees Celsius, and the natural log of the K value that's given, which is from above, 4.5 times 10 to the negative 4. And if we calculate that out, we should get 19.1 kilojoules. There we go. So it is non-spontaneous, it's a positive value. What is the value of delta G at equilibrium? So sort of a trick question. Delta G at equilibrium is equal to 0 by definition. I won't write that in there. All right, last part. D. What is the value of delta G when you have those values for these different concentrations? Sort of like a Q. So we'll figure that out. Alrighty. So again, the whole products of a reactants. I'll just go ahead and write these in. 5.0 it looks, times 10 to the negative 2. 6.0 times 10 to the negative 4. And based on the values that are given, over 0.2. And if we do all the calculations, this is 1.5 times 10 to the negative 4. All right, so we have this information. And again, we have previous information, and we want to figure out what it is at these non-standard conditions. But we have standard conditions right there. So we're going to incorporate this into the non-standard equation right here and solve for with the Q information we just got. Okay, so again, we use this under non-standard conditions. Solving for this, we have 19.1 kilojoules plus, and again, using the equation, what did I do here? I'm looking up, it's like, that doesn't look right. Talking and writing at the same time isn't as easy as it sounds. There we go. 8.314 times 10 to the negative 3. And again, that's kilojoules per mole per Kelvin. and times 298 Kelvin, and natural log of 1.5 times 10 to negative 4. And that's, of course, from above. If we run this calculation with these changing conditions, that will give us negative 2.72 kilojoules. So in comparison, previously looking at that, we had a negative value, a positive value, which tells us it's non-spontaneous under standard conditions. But when I manipulate the conditions around for Q, and I incorporate it into the equation in comparison to what we would expect at standard conditions, we can see the reaction is now spontaneous. There we go. All right, a little bit more on the other side. We'll take a look at those. First one. At 25 degrees Celsius, a 0.01 molar solution of a weak base has a pH of 8. What is the expression for the calculation of the free energy for the ionization of this weak base? And I'll tell you right there, let's do a rice. Yeah, I know you're a little upset that you didn't think you'd be doing rice anymore. It's still out there. So if we're looking at a base, weak base, you're going to add that to some water. It's going to do the whole switching over to the other side, taking a hydrogen with it, and giving us OH. So having this set up, I'm only using this just so I can kind of see what goes where. I'm at equilibrium. I have a pH of 8. So if I have a pH of 8, I know what this is. Not 8, but 6. POH thing, right? So if I have that number, that implies if it came from here, these guys are a 1-to-1 relationship. So I also have this number. And as far as how much this is, it's really, really small in comparison to the original amount. So I can assume it's not really much consequence. So it's still, it's about the same. All right, so I can use the equation we used previously in relating equilibrium, which is where we're at, to delta G. So again, it's asking us to calculate the free energy, or what is the free energy. We can do that under these standard conditions. Natural log of 1.0 times 10 to negative 6, and I made this too big. How about this? Squared. There we go. Squared over 0.01. And if we go ahead and do the math on that, it should equal 57.0. And so therefore that is a positive value. Okay, so it's not a spontaneous reaction in the forward direction. There we go. Done with that one. The last one I kind of like. There's no real math at all, so we can just kind of walk through it talking about it. Ice is placed in a container, 30 degrees Celsius. It melts. I would think so. Describe the situation in terms of delta G, delta H, and delta S. This would be a really good FRQ type question. Delta G, what would you expect? I would expect that value for it to decrease or become more negative because the reaction, we'll call it a reaction, is spontaneous. Okay, let's look at delta H. That I would assume would increase And the reason, again, I'm talking about the system, which is the ice. That should increase because it is an endothermic process. It's absorbing heat from the surroundings. So it's taking energy in. That's a positive value. Delta S, I would say, increases because you're melting ice. It's taking in more energy. It's becoming more random. So the system is becoming, that's a C. Random. And then again, they kind of tie this whole thing together. Delta G is equal to delta H minus T delta S. Looking at how those two for delta H is positive and delta S is positive as well. Putting these together, how is this going to work out here? Because they don't completely go to here. So if this is positive, this doesn't work. If this is positive, it does work. So when does this actually become spontaneous? We're saying it happens. The ice does melt. So this reaction is going to come true when temperature is in our favor. And we'll write that down. Temp is high enough or large enough. And that is for delta S to overcome the delta H value, which is not working in the direction we need it to for this to be a spontaneous reaction. So it's providing for a negative delta G, because we know it is spontaneous. The ice does melt. And just to kind of add one more note here, if at 0 degrees Celsius, the delta H is equal to negative T delta S, something we looked at earlier, and delta G is equal to 0 at equilibrium. In other words, it would be reversible and it would go back and forth. So we can determine the temperature again is 0 if we solve for that equation. The temperature would be 0. And delta G here would be 0, indicating that you're at equilibrium. There you have it. That is the end of the chapter. Those are the problems for the chapter. At your leisure, you should go through those, start answering those, and eventually I'll open it up and you can email me any questions you have on any of these particular questions, and I'll probably try to throw together a screencast, not probably, I will throw together a screencast of some of your favorite questions you have for those. So I'll be paying attention to my email looking for your questions. Okay? I'll give you one more, well, we're good here. Have a nice day.